Hey everyone, here we're going to be building the sampling distribution for a sample means. We'll be using the scenario of sampling some pennies. So here I have my data of all my pennies. So I have, it looks like, here's penny number 1. Its year is from 95. And its age from 1999 seems to be 4 years. Okay, so it looks like the population is of size 1,000. Okay, so we have 1,000 pennies. We've collected the year in which they were minted and the years, how old they were as of the year 1999. Okay, so here I'm going to just be looking at the year in which they were minted. That's my variable that I'm going to be measuring here. Okay, so as you can see down here, here's a graph. This represents the population data. So you can see that the shape of the distribution is skewed left, right? Lots of pennies that were minted close to the year 1999. And very few that were minted before 1960. You can also see the mean of all the data. The mean age of the pennies is 86.736 with a standard deviation of 9.608. Here's the size of the population, which is 1,000. Okay? So what we're going to be doing is building the sampling distribution samples of a particular size. Okay? So what I'm going to do here, I'm going to start creating these graphs here and here that monitor the samples. So here we're going to see our sample data, and then here it's going to collect all of our sample means that we get and start to assemble the sampling distribution. We'll also see mean, standard deviation, and sample size of each sample, and same thing in this sense. We'll see mean of the sampling distribution, the standard deviation of the sampling distribution, and the number of samples that we've taken. Okay? So I want to make sure that our sampling distribution will be normal, so I need to make my sample size 30 or greater. So let's do 40. Okay. So my sample size, I'm going to take samples of 40 pennies from these 1,000 pennies, and we're going to keep track of the mean standard deviation and build the sample distribution. So I'm going to take just one sample at a time going forward, and then we might change that. First, I draw my first sample. Okay. So here you can see all 40 of the pennies that I've selected at random. And so I selected penny number 19, number 399, so on and so forth. Down here we can see a dot plot of the most recent sample, that's this one here, and it indicates what the mean is. So you see our mean is 85.350, and the standard deviation of this sample was 10.001. It also locates them within the population data right here. Now you see here that we have this one little bar. This one little bar corresponds to the sample mean of our sample here. So that would be 85.35. That looks about right. Let's do another sample. So I'm going to draw another one, just one sample of size 40, and I get this sample data. So it looks like my average was 85.25 for the sample. Standard deviation is about 10.19. So here I have another. So here's my another little rectangle. Here's my old one from the previous sample, 85.35. Was the average? Here I have 85.25. That's the average. I'm going to continue to draw a bunch of samples. So you can see, just add in this column here, it's adding the location of these sample units. What it's doing is creating a histogram of these sample averages, right? So that we can see the distribution. So as not to take too long, I'm going to start taking 100 samples at a time. So we take 100 samples of size 4. There we go. So you can see the sampling distribution kind of taking shape now. We take more samples of the same size, we should get closer and closer to a normal distribution, right? And that's because the sample size is greater than 30, so we should expect that sampling distribution should have a normal shape. Not only that, we should expect certain things about the mean and standard deviation. Recall that the mean of the sampling distribution is equivalent to the mean of the population. So let's compare that. So here I have about 86.7. Here also about 86.7 is our mean. Recall that our standard deviation is calculated using the formula sigma divided by the square root of n. So let's see if we take sigma, which is 9.608, and divide that by the square root of n. So 9.608 divided by the square root of about 9.608 divided by the square root of 1.501 gives us 1. I'm sorry, that's incorrect. So remember, it's sigma divided by the square root of n. So 9.608, that's our sigma, divided by the square root of the sample size, which is 4. So that's 1.5 approximately. Standard deviation from the sampling distribution is approximately 1.5 as well. Okay? Now, let's try to take a small sample. So let's say we take samples of size 2 instead. So let's clear this out. So here we're still dealing with the ages of the year of penny. And now we're going to take samples of size 2. Let's draw 100 samples. So as you can see, we have different samples each time. Now, if you look, when the sample size is very small, we don't quite get a normal distribution here. In fact, it looks more skewed left than the population. The central limit theorem cannot be used in this sense because our sample size is just way too small.